maybe enough time has passed, and I don't want to steal like the thunder from the panel discussion, which is maybe the room for these kind of questions. So let Benny begin.
Okay, thank you. So, right, so thank you, Buzz, for organizing this thing, and let me start by congratulating all the authors of these works and all the people who participated in this huge, as Rachel put it nicely, community effort in order to get this amazing thing. Okay, so I'm going to talk about the assumptions and what happens to my slide? Okay, good. So that was my view, I guess, a few years ago about obfuscation. You know, this is like a wonderful castle, and this, you know, it's on a huge rock. Like there are many reductions, many interesting stuff, but eventually it's kind of flying there in the air. And at least for me, right, this was my personal view, and it seems that I was wrong, of course. But it looks like something that you know that whose foundations are not very firm. But this has changed, and now we have we can base it on assumption. In fact, not only one, right? Several assumptions, and this picture is somewhat misleading because you know when you look at this picture, it seems like if you remove one elephant, then you know the rock is still steady. The real picture is something like this. But still, you know, it's much better than the previous state. And we have all sorts of assumptions. I'll talk mainly about this, the work that was presented today. So we have 4 assumptions. 2 of them, LW and SXDH, are, I guess, are well studied. And we can also talk about what it means exactly, well studied, right? But at least if you count the number of papers, they have many papers are used them, and we kind of definitely for LWE, we are used to also for SXDH. This is the pairing based assumption. And there are 2 relatively less traditional assumptions. One of them is local PRGs, and the other one is LPN. And as Zvika pointed out, this P, you know, stands for parity, so it's not a good name unless you think about ModP. And this, it's not learning parity, it's learning PRE with noise or something like this. Anyway, we should find a better name. So these are the 2 new kids on the block, and I'll try to talk mainly about these 2 elephants. Chris said the same thing. Thank you, Chris.
So Benny, there's a question. Does the size of elephant represent anything?
Not now. Eventually, I'll try to order them, and this is actually a challenge for you guys. Try to order the elephants. I can ask one clear order is, you know, who was first, right? I mean, all these assumptions were made in the 21st century, right? After 2000, who's the oldest one, right? I mean, that's kind of, I don't know, a riddle. Think, and I'll let you know later. Anyway, just, I mean, before we dive in, let me just point out, as Amit said, and I think that Yael also mentioned, these 2 guys are public key encryption assumptions. And in fact, they are kind of strong, they assume strong homomorphic properties. If you follow in Pagliazzo and generate a new word, I would call it like a homotopia. And on the left-hand side, these are kind of private key and mini-crypt assumptions, but they actually talk about the easiness of generating pseudo-random bits. So this is kind of fast mini-crypt assumptions. I'm not saying that they are more plausible, but I mean, you'll be the judge. Okay, so I'm here to talk about the elephant in the room, right? So let's talk about the elephants. So let's start with the learning parity with knowledge. This P is really stands for parity. So in this version, it was presented by Blametal. This was Crypto 94. So you have a small box. Inside it, you have an n-bit vector S. And you can push a button, and you get a sample, a random n-bit vector A, and the inner product of A and S. Well, not really the inner product. It's a noisy inner product, right? I mean, actually, okay. Let me try to find a way to see your faces and the slides. Is there a simple arrangement? Maybe something like this. Okay. So
you can
this.
stop full page if that helps. I don't know.
What?
No, I'm not sure. I'm not sure it actually works when you're presenting mode. But if someone asks something in the chat, I will. But people also should feel free to just unmute themselves and ask questions.
Okay, good. Yes, ask. At any point. So okay, so this is a noisy product, right? I mean, you flip the bit with probability epsilon, and this epsilon is smaller than half. Okay. So you can push the button again and see another sample and another noisy bit, and so on and so forth. And at the end, your goal is to learn this parity function, this vector S. Okay, so this is the learning parity with noise as it was presented in BFKL. But actually, and again, I'm going back to Amit's talk. I think that it's nicer to think about this problem as a coding problem, and the reason is that when you talk about in terms of learning parity, you don't really distinguish between the time complexity and the number of samples that you get. Okay, and this is actually important. So let's think about it as a decoding random linear code problem. And surprise, surprise, this is pre-90s. This is Goldreich et al. So they suggested it as a basis for a one-way function, for a regular one-way function. So in this formulation, which is completely equivalent, you're given a random n by n matrix, right? And someone you think about it as a generating matrix of a code. And someone took an information word, this is the vector S, multiplied it by this matrix, added this noise, this is IID noise vector, each coordinate is 1 with probability epsilon, and gave you the noisy code word. And your goal is to decode this code, or if you want, like do ML decoding, right? Maximum likelihood decoding, and recover this information word. In fact, I said 88, but in a sense, you can, if you think about just the crypto literature, you can actually trace it back to McLeese paper in 78, right? So this is kind of 10 years earlier in the beginning of public key encryption. In fact, McLeese public key encryption is the first randomized encryption scheme, right? Before we knew that randomness is necessary. So it's an old basic natural assumption. And it's information theoretic solvable when n is sufficiently large. So how large? Without noise, slightly more than n should be enough, right? I mean, this matrix should be invertible and S will be fully specified. When you add noise, you have to pay some penalty, some overhead, which is kind of proportional to the entropy of the noise, right? So this is, again, this calculation go back to Gilbert. And it's not hard to know that when m grows, the problem becomes easier, and when epsilon decreases, also the problem is easier, right? So you can prove, it's an almost trivial statement that if you can solve LPN with parameter m and epsilon, I'm thinking about m is always larger than this threshold for this talk. So you can solve it for these parameters, then if you can also solve it for larger m's and smaller epsilons. And the reason is that you can always ignore some of these equations, right? So ignore this m prime, and you can always add noise, right? If this noise is too little for you, add some noise and then solve the original problem. What about the complexity of solving this problem? Well, you can do exhaustive search over this information word. This will give you 2 to the n. This will be trivially in 2 to the n, but you can also enumerate over the possible noise vectors. And this is actually an important observation we'll see later. And right, I mean, so all these vectors, all m-bit vectors of weight roughly epsilon times m. So this will take you something which is exponential in the entropy of epsilon times m. And this kind of the fact that you have two alternative kind of secret keys, if you want, two alternative things that can be solved is really useful in many applications, right? I mean, you can either solve for S or solve for E, right? Both things will give you a solution. Okay. Chris is asking questions, but I don't see it. Just saw that he asked something. Chris, just speak.
Yes. Okay. Sorry. Is it enough also to just enumerate over n entries of the noise vector as long as it's
good
2n or something like that, or is that not trivial? Is that not?
That was trivial, and here's another. This is kind of a variant of your attack.
Okay.
This is the probabilistic variant. You can play and hope that the first n coordinates are not noisy. Okay. And this happens probability 1 to the 1 minus epsilon to the n, and then solve it using linear Gaussian elimination.
I think Chris was asking something else. He was just pointing out that it's basically also like 2 to the n, right? Because you only need the h of epsilon. You only need the first n over, or it's like n times h of epsilon over 1 minus h of epsilon, right? Because you only need the first n over 1 minus h of epsilon entries.
Maybe another way to say it is you can take n times 1 plus epsilon, choose n, so you can guess. You can enumerate. You take the first n times 1 plus epsilon equation and try to guess the.
That's why I said to the last line here, right? I mean, you could just try to clean the first n equation, so find the n independent equations and try to clean them. Okay, so there you have a. And as Amit and Chris know, you can actually move this S and make it sparse, right? This will give you the same effect. Right? This is in ACPS. Good. So these are kind of trivial things that you can do. Let me mention that you already see that if the noise rate is 1 over n, then this thing is solvable, right? Efficiently solvable. So you cannot have the noise cannot be too low. So let's look at this kind of graph. So here I have the number of samples, right? It grows when you go up, and this is the noise, and the noise grows up to half. Say when the noise is half, right, you cannot solve. This is just a random vector. Information theoretically, S is cannot be found. So let's look at what's known. So I'm I didn't list all possibilities, but there are two important regimes for us. One of them is kind of the constant noise regime. So I just wrote a quarter, but you could think about other constants. This is kind of constant LPN, and the most conservative setting is when you have constant noise and linear amount of equation. In fact, you can think about something even more conservative when the constant is really approaches to half, but let's ignore this thing. Okay, let's think all constants are the same for this talk. So this is one regime. This is I guess the most conservative one. You can also think about the poly regime, where the noise is inverse polynomial, and there's a difference between the differences parameters here, but let's treat them for a second as a single regime. So the noise is 1 over poly, and the number of equations is also poly. Okay, so this is another regime. And there's an easy regime where the noise rate is very small. It's kind of polylog n over n. And it's not really simple, but I guess trivial or almost trivial regime when you get an almost exponential number of equations. Okay. If you were running in polynomial time in the number of equations, then I would call it maybe xn would be trivial. So let me tell you what's known about these regimes. My slides are stuck. Okay. No. Okay. Okay. Good. So let's start with this area. So here, the best thing that we know is the exponential time. Okay, so if you have a constant, like a linear number of equations and a constant fraction of noise, we don't know anything better than exponential. Still, there are interesting things to say about this regime. There are non-trivial attacks. In particular, I think that the constant here can be something like 1 over 20. And also, there are interesting implications. So this is kind of a mini crypt assumption, but still there are things that we can achieve here, which are not known to follow from general one-way functions. For example, we can get a one-way function with locality 3, which is kind of optimal. That's what we did in AIK. You can also get all sorts of cyclic secure encryption schemes in the private key setting. and KDM secure encryption scheme. So it's kind of, it's a mini crypt, morally it's a mini crypt, but still it has all sorts of applications. If you go up all the way here, then this is the Blum, Kalai, Wasserman celebrated result. You can actually, given like almost exponential number of equations, you can actually solve it in almost exponential time. Okay, so this is a minor shaving, but we don't know anything better than that. And if you go and allow only a polynomial number of equations, then the shaving that you get is more minor. This is due to Vadim's paper. Basically, it shows how to take such equations and lift them up to this setting, this number of equations. And in fact, both algorithms here work even when you are very close to half. Okay, but you don't see it in the slide.
So these are binary LPN attacks?
Binary LPN, right. I mean, I'm starting with the classics and we'll move to the more less standard, the less standard thing on the new stuff later. Okay, so let's start with the binary. In this regime, you can actually get a sub-exponential attacks. I'll show you how in a minute. But this regime is, I guess, it's less studied. And as Amit said, there's a difference between these different parameters. So if the noise is 1 over square root 10, then we know how to get public encryption. We don't know how to get it, say, when the noise is slightly more aggressive. Okay, this is due to Olechnovich. And I should say, if you go up from linear to polynomial or even sub-exponential, we don't know anything better in this regime. Right? It's not like we have some jump in the complexity. Again, ignoring the exact value of delta, of course, which will depend, which will shrink.
So,
in this regime,
sorry, Benny, the delta is like in a mid stock. It's the n to the delta is the noise, yes?
No. I didn't like, this is like a very rough sketch. I didn't relate this delta. This delta will depend both on the noise, and also it will mainly depend on the noise, but it also depends
the same
on equations, I guess.
Okay.
I mean,
so it's a function of the delta of the noise, but it's not equal to delta of the noise.
It's not equal to the amount of noise, although the best known attack, I think that this will be a good approximation, right? I mean, you will get something like n over epsilon. We'll see it in a minute.
Okay.
Good. So in this area, right, it's clear that this is quasi-polynomial, right? I mean, just enumerating or trying to find the noise vector, it's quasi-polynomial. But even here, there are interesting things going on. So the log n over n regime, we can actually solve it in polynomial time. Somewhat similar to the setting where in graphs, you can find small log n graphs by using color coding in polynomial time. So you get some saving, right? I mean, you could imagine that this would be like n to the log n, but it's not, it's polytime. And in this regime, Tzvika et al. Showed that you can actually, at this point, you get SDK hardness. So this is in SDK, and you get worst case to average case hardness and so on. So let me mention.
That's SCK easiness, right?
That's
SCK easiness.
Yes, I mean, if SDK is easy, then good, yes, of course. If SDK is easy, then you can break it, right? Let me just mention why I'm putting it on the slide. For most public key encryption that we have, if you assume that SDK is trivial or something similar like NP, intersect NP, if you get an oracle for this kind of thing, then you can break the public key encryption. And this public encryption is, I think, one of the few that I know that we don't know how to break given an SDK oracle, right? So I don't know. That's one of the things that makes this assumption so interesting. Good. Let me show you a simple attack. It's kind of a distinguishing attack, and it's not an inversion attack. And I think that in a sense, like Amit had this slide with a huge number of attacks. I think that all of them eventually use some variant of this thing, of course, plus many other tricks. So our goal is to distinguish A, B from A, uniform. Okay, so let's kind of do this. And here is the idea. Let's find a small set of linearly dependent rows. Okay, I'm not saying how to find it. This is actually the most complicated part, for example, for BKW and the other algorithms, how to find such a linear dependency. But let's assume that I have it. Imagine that I'm allowed to do some pre-processing that depends on the matrix, right, for free. So I have this small set of linear dependent rows, and I'm going to look at the corresponding coordinates and output XOR. So this is my distinguisher. Okay, so let's try to analyze it. Okay, so I can think about this set as just as a vector V, right, which is in the co-kernel of A, right? It's orthogonal to all the columns of this matrix, right? And let's denote its weight by delta. Okay, kind of it's a low weight vector in the, if you want, in the dual column. And now, when I outputted this B, this is basically, right, the inner product of V times B. But if you look at the left-hand side, when you take the product of V times this thing, well, there's the code part. This zeroes up, right? Because this is kind of orthogonal to all the columns, and this vector is in the span of the columns. And what remains is just V times E, right? This is linear algebra. So what's the bias of this thing? Well, of course, this bit would be uniform if this vector was random. But when this is pseudo-random, we basically took the XOR of delta entries here, where each entry is a random coin, right? It's a Bernoulli random variable with parameter epsilon. So we know how to compute the bias of this thing, and the bias is kind of exponential delta over epsilon. Okay, so this is the advantage of this attack. How small this delta is? Well, roughly, and again, I'm ignoring kind of log factors because this thing behaves differently when an M is linear or not. This is basically N, and I can shave from N something like log M. So you can see that this shaving factor is really tiny even when M is huge, and the epsilon. Okay, so when I have sub-constant noise or like inverse polynomial noise, I get something non-trivial, right? I get some distinguishing advantage, which is kind of a 1 over poly and not exponentially small. Oh, sorry, not the 1 over poly, but exponential in n to the some 1 minus delta, and not exponential in n. So if we ignore the complexity of finding V, the overall complexity of this attack is roughly this number. And as I said, many fancy attacks are devoted to finding this V. So this gives us some sort of a natural lower bound for the ability to break this assumption. And this is different from previous algorithms. When you look at, say, M, which is like 2 to the square root of n, this prediction gives you something better than BKW. It says that you should be able to break things in time 2 to the square root n, for example. And the bottleneck indeed is finding this vector. Right? This is the hard part. We don't know how to find such a low weight vector, and the techniques of BKW, like the birthdays and the bucketing tricks, actually need a much larger number of equations.
Okay. Benny, I got a little confused. What do you mean by how small is delta? You mean how small is delta such that this small vector even exists in the kernel of A? Is that what
I'm saying? Like, remember that right now the matrix is random. So you can kind of analyze what is the expected size of delta, right? I mean, for a random matrix, right? I mean, and this is what the expected size of delta as function of n and m. Right? This is just a very simple calculation, right? I mean, you compare the probability that delta rows will be linearly dependent with the union bound over all possible delta rows. This will give you.
So the way you define delta is just the smallest vector in the kernel, and you're asking how small is what is the expected value over a random A.
Right.
Thanks.
And you can see, going back to obfuscation, if you think like we're still over the binary field, but if you think about the polynomial regime, then this will give you like a sub-exponential hardness. At least if you know, we don't know that this is the best that you can do, but this is the prediction of this kind of heuristic. Good. You know, we kind of looked at the pseudo-randomness, but in fact, you can show that pseudo-randomness is or search, the search version, the LPN version, implies the pseudo-randomness version of the problem, right? Or in other words, if you can solve the pseudo-randomness problem, if you can distinguish, then you can invert. This was first observed by Blum et al. And let me show you a proof from AIK that preserves the number of samples, like the original proof had a blow up in the number of samples. Okay, so the idea is kind of simple. Let's assume that search LPN holds. Then by Goldreich-Levin, it's how to approximate the secret, the inner product of secret with a given R for random vector R. Right? This is a Goldreich-Levin hardcore bit. So I'll show you how to use your distinguisher from for pseudo-random for the decision version of the LPN to compute the hardcore bit. Okay, so let me show you how to do it. So I'm giving this pseudo-random distribution A comma B, a noisy code word, and I'm giving the R, the Goldreich-Levin randomness, and I'm going to do the following thing. I'm going to re-randomize this matrix A, I'll show you in a minute how, and define a new matrix C. Okay. And with the property that basically, if the inner product was 1, then this pair is uniform, and otherwise this pair is still comes from the noisy code word distribution. Okay, and therefore a distinguisher will allow me to approximate this hardcore bit, or to predict the hardcore bit. So let me show you how to do this kind of step, how to generate C. So I'm looking at this vector R. I'm looking at the coordinates, the support of these vectors, right? I mean, I'm thinking about these things as pointers to columns of A. I'm going to sample a random fresh vector V, and I'm going to add this vector, the same vector, to all the columns that are pointed by R. So this is my new matrix C. Okay, and now let's see what happened. Okay, so when you take the product of S with this C, well, you get the B, and you get some extra term. What is this term? Well, basically, it's the vector V, but it's added, like I have a constant here, which is the inner product of S and R. And it's easy to see it either by doing the linear algebra or by thinking, you know, if this S was orthogonal to R, then basically when you add all these columns, you basically add them the columns an even number of times, and therefore they kind of vanish. Right? So just by opening the parentheses, you'll get this thing. And this means that if the inner product was 0, then I didn't add anything. So this is still a noisy code word, right, B. And if this was 1, right, then I randomized B, right? I can move it to the other side and then look at B as a noisy vector plus a fresh random vector V, which means that this thing is truly uniform. Okay, so this is the idea.
And isn't there even a simpler version of this proof where you just go over all the rows and you say you search LPN on the n-1 rows, and then argue that by Goldreich-Levin the last row is random, and then just do this for each row to replace all the bits of B by uniform?
I'm not sure. Like again, what I was saying. So there is a simplest version, but it costs you more. It has an overhead. Right? You could say I want to let me move. Okay. You could say I want to recover just the first entry of S. This is what the BFKL did, and then you kind of add a random column to the first column here.
I'm suggesting even something simpler. So think of the first n-1 rows of AS plus E. And the first n-1 samples out of the LPN samples that you have here. Mm-hmm. And essentially think of that as a search LPN problem. So by search LPN, you know that it's hard to recover S from the first n-1 samples. And okay, then you say the last sample is just a Goldreich-Levin bit, even plus noise, but let's ignore the noise.
Good. And so you're using the unpredictability trick. You're right. I think that it will work. Again, you will lose the factor, right? I mean, when you move from unpredictability to pseudo-randomness, you lose a factor, which is the length of this vector. But if you think about it as polynomial, then it's okay. But you could think of longer values, and then your thing will lose too much.
And I guess if that fits on a slide, that's okay.
What?
I guess it's not that bad because it still fits on a slide. So even if you can simplify it more, then it's not that bad.
Yeah. I mean, I think that this is like, you know, we didn't even think about it as a result in AIK07. It was kind of a simple lemma, but then we realized that, I don't know, the people may want to
and Chris is commenting on the chat that maybe something similar, a similar argument was used for subset sum by Impagliazzo and Naro in 96.
Maybe it's plausible. I'm pretty sure that this argument was used, and it's very robust, and it can be used in several places.
Yeah, one interesting thing about the Impagliazzo-Naro version is they didn't have any modular arithmetic in subset sum. And so instead of guessing R inner product S, they're guessing R inner product S over the integers, which is not 0, 1, it's maybe 0 through n or whatever the dimension is.
Good.
And they have to guess that, and then it goes through. But it's a cute version of this argument too.
Excellent. So we'll get back to this point exactly when we move to the mod Q thing. Good. Excellent. So let me point out again, this is kind of simple stuff, but just to get friendly with this assumption, we have an obvious random self-reducibility with respect to S. I think that it appears in BFKL. So say that I want to find S, I can always generate a random code word just by taking the product of a random information word with A and add it to B. This is kind of B prime, and now I basically randomize the S part. Okay, so solving the thing over the zero vector is like solving it over a random vector. This is the same. Another nice observation, I think that goes back to Stern somewhere in the 80s. You can think about the problem as syndrome decoding. Okay, so what do I mean by this? So by the fact that we have random self-reducibility, you can suspect that S is not very important here, right? So let's throw away S completely. So this is kind of the syndrome decoding version. You have a parity check matrix, and you multiply it by the noisy vector, and then you give me the result, and my goal is to find the noisy vector. Okay, so there is no S part here. And it's very easy to show that the two things are equivalent. So let me show you that this thing follows from this. So I have A on my hand, so I can always compute a parity check matrix and multiply it from the left. And indeed, just like 2 slides ago, this part will vanish. And the thing that I will get is just the parity checks times E. So when I apply the parity check to B, that's exactly what I get. I will get the red vector. Okay. And so this is a simple observation. It shows that that's another way to generate a pseudo-random bits. But it's actually very useful, as the LWE people know, and as Alekhnovich noticed. So this means that you can actually plant a short vector in the kernel of a matrix, of a pseudo-random matrix, right? I mean, if you add this column to this matrix will be pseudo-random, right? Because we said that this thing was pseudo-random, but now I have a short linear dependency over the columns of this matrix, right? I'm just going to add 1 here, okay? And this is very, very useful because this can be used. We said that if I have a short random vector in the kernel, I can actually break the LPN or get some non-trivial advantage. And this can be used to get public encryption, right? I mean, basically for the right parameters, right? I mean, that's what Alekhnovich did. And in a sense, you can think about all sorts of public encryption schemes over lattices that have this form. And with Boaz and Avi, we had one of the variants of this thing. So put this thing as the public key, keep the short linear dependency as your secret key. And when you want to encrypt, let's say that you will encrypt either by sending uniform or a noisy code word. And this knowledge of the secret key will allow you to at least distinguish with some advantage. Right? And now it depends on the parameters whether this is sufficiently good for decryption or not. And 1 over square root 10 turns to be the magic point, at least for LPN. Okay, let me summarize what we learned so far. So what do we have like evidence for hardness? It's a search problem, which is good, right? Remember that there were days where people said DDH, but we want it under CDH, right? I mean, there was such a thing like, DDH was considered to be a wild assumption because it's a decisional assumption, right? I remember these papers. I read the paper during my PhD. Right now, if it's not bilinear, you don't even, right? So search problem is good, right? We should remember this.
I think DDH was exotic and
yes, I think that I think that in Moni and Omer papers you can see justification for DDH, like long paragraphs that try to justify the thing. So another intuition, well, Gaussian elimination seems to be noise sensitive, right? I mean, that's kind of the basic thing. We can solve linear equation. We have basically a single technique for it, and this technique is really sensitive to noise. As Amit said, it's well studied both in the learning and coding community. To be fair, for some parameters, I'm not sure that coding people looked at like inverse polynomial noise. It's definitely not in the mainstream. But still, you know, you could hope that people looked at it, and in a sense, it gives you a win-win result, right? I mean, if this problem is easy, then you'll get some progress, right? And like, I don't know, if DDH becomes easy, it's not clear how the world benefits from it. Here, you can really use it for doing good things. And you can actually use kind of insights from learning and from coding to prove, people didn't do it, but you can prove that this thing resists all sorts of limited attacks. So it's very easy to show, for example, that the output will be k-ways independent, okay, which means that you defeat AC0 algorithms. It's very, very, very robust. I show you the search decision, but it's also leakage resilient, and you can talk at all sorts of variants of the problem, and the problem still remains hard. Part of the reason, maybe it's related to Daniel's suggestion, this operation of multiplying by matrix is really actually very good, right? It's an extractor built in and a hardcore bit and so on. So you get all sorts of robustness properties for free. And as a bonus, it seems hard for quantum algorithms and even for CoAM algorithms, right? So it's really, in this sense, it's really a good mini-crypt assumption. And this is not well defined, but I feel strongly about it, so I put it in the slide. Like, basically, this is a very simple mathematical domain. So if there was a shortcut, one could hope that we would discover it. Right? Unlike other more complicated domains, like compare the best algorithms here versus the best algorithm for factoring, for example. So there are highly non-trivial algorithms for factoring or even for lattice problems. And here, basically, BKW is a beautiful algorithm, but you can teach it for undergrads in 2 hours. It's really based on very simple ideas and techniques. So one could hope that here in this domain, it's kind of, it's less likely that significant algorithmic shortcuts will be hidden. Features, so it's very simple algebraic structure, almost linear functions. That's what is being used when you prove KDM security, cyclic security, and all sorts of other things. And it's computable by simple bit operations. So people try to push it for like kind of, it's friendly for hardware implementations and so on. Variants. So one variant that is interesting for me is not relevant for this talk is the under constraint case, where you basically below think about the least decoding regime, right? Where there are exponentially many solutions and you just try to find one of them. This is basically what gives you hashing. And
can I ask a question, Benny?
What?
Can I ask a question about the previous slide?
Yes,
so,
please.
You know, this, I think it's a great, actually, the summary. But this thing that you're saying, that the fact that there's sort of a generic, you didn't use the word generic, but you know what I mean, the Blum and so forth, Kalai-Wasserman algorithm, rather than using, like in factoring, sort of the fact that it lives over different worlds. But in the obfuscation construction that was described this morning, there's several assumptions. Right? There's an assumption about LPN, assumption on LWE. What does that mean then? The fact that you have present, in addition to the LPN problem, there's also other things that are assumed. And what if they fail? What if I probably could answer my own question, but it's much easier to ask you because it just popped in my head. So the fact that you have this extra information around, what does that mean? It's not generic anymore. There's other.
So actually, okay, two answers. First of all, of course, like, you know, they need a combination of assumptions. And I had, you know, one of my first slide had this elephant standing one on the back of the other. Like you need all of them to hold simultaneously. On the other hand, I should say the way that they use it, it's actually like things are independent, right? I mean, so you don't need some correlation between the assumption, which sounds like something like shaky or suspicious. So I don't know. It's a combination of this assumption. We'll talk about them. Actually, their assumption, their construction is not about LPN, right? We get to this mod Q thing, which I think deserves more study. Yeah, but I agree. They need all sorts of things, and you need them all right now.
So there is auxiliary input in a sense, auxiliary things that we know about it.
So I don't think that this is an issue in their construction. That's actually not okay. They are careful enough to make sure that things are in this aspect that it's completely kosher. It's independent. You don't have to assume all sorts of that you have LPN security even when you have some leakage or some auxiliary information. This is not something that you need.
Okay.
Okay. So I mentioned the under constraint case. Relating it to the to the standard version is a wonderful question. I don't know how to do it. It seems like these two things are related, but it's not clear. You could try to change the matrix distribution. In a sense, we're going to do it later. But let me just mention that if you are going to do it, make sure that the distance does not, or the dual distance does not shrink too much. Okay, that's kind of something that you have to make sure. Noise distribution. You could think about, instead of IID, just generating a fixed weight, a random fixed weight vector. This is okay. I mean, you can reduce between the two variants. This is not an issue. You could also think about structured noise, which is more tricky. And if you're not careful enough, you may be able to kind of break the thing using linearization attacks, like Aurora get. Larger alphabets, good. So here we have two choices. When you move to mod P or mod Q, either Gaussian noise, this is the standard LWE thing, or using Bernoulli. Okay, and that's what they do. So let's move to this thing. So this is LPN over ZQ, and like Tzvika, I don't like this P for parity. We'll change the name in a second. So this is our first elephant. So what happens here? So we already saw this assumption. The matrix, the vector here are chosen randomly from ZQ. The noise is kind of interesting. So with probability epsilon, you kill the coordinate completely. You add a uniform element from ZQ. With probability 1 minus epsilon, you add nothing. So it's an all or nothing noise, very different from the LWE thing, where each coordinate gets some noise, but a small amount of noise. Well, I said that this is a weird noise, but actually for coding people, this is very natural, right? This is just decoding over the QR symmetric channel. This is more natural than, adding maybe Gaussian. I don't know. I mean, coding people also look at Gaussian. So let me point out something which is very interesting. Say that I wanted to give you a hint, in order to break this thing, this say pseudo-random generator. It suffices to tell you just the support of it's not X, it's E, the support of the error vector. I just give you the location of the noise, and this is kind of this is a sequence of Bernoulli variable. Right? Just telling you whether I'm in the top case or the bottom case. So it's a sequence of bits. So you have kind of an arithmetic assumption. We work with a mod Q, but I can give you a sequence of bits in order to break it. And this is a very interesting property. And you can kind of use it to lift kind of binary crypto to arithmetic crypto. This is how the assumption was first formalized by Yuval Amit and Manoj. They were kind of trying to understand what are the possibilities of doing kind of arithmetic MPC, but in a setting where you have two parties, right? Where arithmetic MPC, we know how to do it when you have many parties. This is naturally what happens when you use like BGW type techniques. But they were asking about two parties, and they use this kind of property in order to do it in the two-party setting. And later, like we kind of formulated the whole notion of what it means to have arithmetic cryptography. This is with Chris and Lior Zichron, and sorry, Jonathan Avron, different student. And And there also, this thing, this kind of, we could abstract this property and abstract the kind of primitive that allows you to lift from binary to arithmetic. This is like a very useful thing. And I don't think that we have many other options or many other alternatives to this thing.
So Benny, is this related to your work also on MPC where you go with the rounds?
No, not related.
So there you have a binary to arithmetic stage, right?
But there it's all information theoretic. Here, this is really like the use of computational assumption.
Yeah, okay.
Let me say, okay, so
it's for a different Simon's workshop.
Maybe. Okay, so I like to call this thing random linear code, and so these are the parameters. And here we have two versions, and as Amit said, we don't know equivalence. Or maybe, let me say it more precisely, we know like the hardcore bit that I mentioned previously works, as Chris said, but you can actually use it as an oracle that checks whether the inner product equal to some fixed element in the field. So you have to pay the size of the field, and when Q is super polynomial, the reduction is not polynomial. And this is a wonderful, I think, question to try to make it polynomial even for large Q. I should say that when Q is non-prime and it's a smooth integer, then you can use CRT and still do it in polynomial time, right? Good. Is it hard? So it seems as hard as the binary version, right? I mean, if you look at the attacks that we have, we don't know how to exploit the fact that we work over larger modulus. And again, the intuition is that noisy algebra is hard. You cannot, as Boaz said, you get a lot of information, but unless you know that this equation is clean, then once you know that an equation is clean, then you get lots of information, right? You get the whole symbol, but without knowing it, you don't know how to extract partial information, at least using current techniques. And in fact, some attacks, in some sense, it becomes harder, at least if you look at it in attacks. So some attacks kind of make use of the fact that when you add the two noise vectors, you get some cancellations in the binary setting. And when you add two noise vectors, mod Q, you will not get cancellations, right? I mean, two noisy coordinates will remain noisy. So this is, I don't know, this is the good news. I should say, I don't feel that we understand the dependency on Q good enough. I mean, and as Boaz asked previously, I kind of suspect that when Q is super large, we should gain something somehow, but I don't know how to prove such a thing, and I think that it deserves more study. Let me point out to something very powerful that goes on here. Like, as I said, if you look at the effective secret, how many bits I have to tell you in order to break this thing, it suffices to give you, let's think about a constant noise for a second, a linear number of bits, just to tell you the locations of the noise. But the stretch here is omega of n field elements. So I get a huge number of think about a large field. So I get a large number of pseudo-randomness, but in terms of secrecy, it's kind of weak. Now, there is no paradox because you also invest all this, when you add this noise, you also invest random field elements. But still, right? I mean, in a sense, the effective hardness is only n bits. So I don't know. I'm not sure how to articulate this thing, but this is, I think, a very interesting property. It's also related to this lifting from binary to arithmetic.
Benny?
Yes.
We also don't have any modulus switching technique for this noise model, right?
Good. No, we don't. So yes. So for example, try to compare two modulus, right? I mean, we don't know how to compare them. It seems incomparable. And at some point, I was hoping to use this assumption in order to kind of relate binary LPN to LWE. Right, in order to at least import something from one domain to other domain. This seems like something in the middle, but I wasn't able to do it. And then we'll get, I mean, part of the fact is that we don't have any, at least as far as I know, we don't have geometry here in a sense. Okay, we'll get to it in a minute.
One more question, Benny. So there are these variants in LWE literature, at least, like what if the secret is binary vector, but like seen over a large modulus? What happens in this like LPN over ZQ where the secret, let's say, is chosen from binary domain? Does it make it any easier or harder?
Good question. So you could probably get the secret to be sparse. Like the ACPS transformation should work here easily. So you could get a secret which looks like the noise distribution. But if the value of the secret is 0, 1, I don't know. I don't think that it was studied. The whole thing was not studied too much, right? Now we have a good motivation for it, but I don't know.
Another question along those lines, and probably also the answer is it wasn't studied, but I'm just wondering, what if instead of looking at ZQ, you look at the field of the of size 2 to the L or 2 to the whatever K? So in that case, there might be some connections between that and this traditional LPN. Is anything known there?
So I have a vague memory that I tried to look at it like actually when I was in Princeton, but I don't remember what were the conclusions. I suspect that it will not be hard when you work modulo like a small prime power, but I'm not sure. I mean,
you still have noise, right? So
what?
There is still noise, right? So it's interesting maybe to understand if you just think of instead of ZQ F2 to the power K. So it's kind of like structured noise.
You probably could just, I think you could just trace down to the prime subfield, and then you would reduce to the, to the prime subfield case. So it's no harder.
It's no harder than LPN with parity. Yes,
yeah.
No, that's easy. You can take the least significant bit and forget about everything else, right?
Yeah, you could just take every coordinate. Yeah, you could. In every block of size K, just take the first coordinate and ignore all the rest. But
so I don't know. Many cool questions, and some of them maybe are not that hard. I don't know. Like,
is there perhaps if the coordinate wide error is bounded from below, is there perhaps something known? So you get like chunky errors, so to speak.
I'm not sure that I understood. How do you think about the error distribution?
No, so instead of instead of 0, 1 errors, which somebody suggested, you could have errors that are maybe larger than Q over 2 always.
I don't know. This sounds like a different. So sure. Again, you're talking about the magnitude of the noise. I'm not sure that I follow.
Yes, magnitude of the noise. Yes.
Okay, so the whole thing here is that there is no magnitude. Right? That's the main point of this variant of the assumption. Actually, I'm not sure how am I doing with time. I think that I'm. When did we start?
Yeah, I think we started like 5 minutes after. I don't know how much more time do you need?
Well, tons of time, but when was I supposed to finish? Now?
Theoretically, about now, but we can.
Okay. I don't know. Okay, so let me try to kind of do it faster or something, and skip many things. Okay. LWE, Regev, mainstream crypto assumption, noise induces geometry. Very different game, so it seems at least. Let me skip this stuff. I mean, there are. This is kind of read one of the surveys. Let me say that here, this is as hard as worst case lattice assumptions, and basically the important thing is that the approximation factor is n over the epsilon, right? Where epsilon is kind of the width of the Gaussian. So right. Okay. Skipping. SDK, unlike the previous version. Okay. So I have to decide what to say now because I don't have time. Okay, let me tell you like the short story about local PRGs, although there are many things to say. So local PRGs, we mean that each output bit depends on a constant number of inputs. The function is kind of defined by a graph and the list of predicates. And for our talk, it's kind of, you can think about a single predicate that kind of computes each output. Long line of works, I wrote a survey, read it if you're interested. The stretch really matters here, okay, unlike other things. So if you want just a tiny stretch like n plus square root n, then you can get it basically based on any one-way function in NC1 or even variance of log space. This follows from basically every cryptographic assumption that we know. If you want linear stretch, we can get it from LPN over sparse matrix. So this is kind of an assumption made by Alekhnovich. So think about a sparse matrix, and again, constant amount of noise, and then linear number of equations. So as I said, you have to make sure that the dual distance is not too small. And indeed, Alekhnovich made the restriction that the matrix represents a good expander graph, which implies that the distance is good. And this thing looks local, right? I mean, the matrix is sparse, still there is the noise. The noise is not local, but still you can kind of do all sorts of things and get a pseudo-random generator. That's what we did in AIK07. And there are all sorts of really cool connections between this problem to CSP problems like Feige's refutation assumption. I should say that if you want linear stretch, you can base it over also on other assumptions, like for example, take arbitrary matrix, not necessarily sparse. If you assume that the problem is exponentially hard and the linear mapping S times A is computable in linear time, and we have candidates for such matrices, then you can get linear PRGs in NC0. So this is, you don't see sparsity in this assumption. Generic attack. So note that if you have a set of outputs that is shrinking, namely it connects to smaller number of inputs, then you can break it easily. Let it just ignore all the other outputs and just break this PRG, right? So you can enumerate over the k bits, right, of this seed. So this means that you must assume expansion in the graph. Still, for linear stretch, you can get linear amount of expansion, and this is plausible to be exponentially secure. Okay? We don't know better attacks against this kind of candidates. Polystretch. So this is another elephant that is being used by the obfuscation. So here we think about m equals n squared, and in fact, you know, whenever you have something which is kind of larger than 1 here, then you can get an arbitrary constant here if you by increasing the locality. So this whole class of superlinear is kind of equivalent in a sense, if you don't care about the exact locality. So in this regime, you can also, on the just expansion, you know, if you look at the graphs, you can show that you cannot get linear expansion. So the expansion will be smaller than n, which means that you can get only sub-exponential security. And here, in fact, finding the non-expanding set is actually hard because you will get many sets like this. And for this regime, you will find something sublinear. Morally, we should be able to get this by assuming kind of sparse LPM with sub-constant noise, right, in terms of entropy, but we don't know how to do it. And the only thing that we know how to do is based on the Goldreich's assumption. So let me just mention the assumption and say what we know how to get and conclude there. So Goldreich original assumptions say the following: take a graph with n inputs and m outputs, and take a random predicate, right? Fix it in all the locations. The inversion should take time which is exponential in n. Okay, so he talks about the inversion complexity, not about pseudo-randomness. And for this kind of discussion expansion, let's say that it means that some omega of n outputs, every set of say n over 3 outputs touches many inputs. And basically, it's interesting that expansion arises here because Goldreich's kind of reason for looking at expansion was very different from the reason that I showed you in the previous slides. It was kind of looking at divide and conquer approaches, and you can see that if the graph decomposes easily, then you can do divide and conquer in order to invert, and basically expansion is kind of the opposite thing of being decomposable. And he was even able to prove that some attacks takes exponential time in the expansion parameter. Let me skip this thing because we don't have time. You could try to generalize this assumption to longer outputs, and here is the one-wayness version. So for properly chosen predicate, here you cannot assume random predicate anymore. This will not be true. Any graph G, well, it's hard to approximate this thing with complexity, which is exponential in the expansion parameter of the graph. You have to define what is the expansion parameter, but let's leave it. Okay, so this is a reasonable assumption. It's parameterized by this M, by the predicate, by the locality, and by the expansion quality. And let me skip obvious things. We can actually prove that this kind of assumption holds with respect to many limited attacks. Okay, some of them are very interesting, and the proofs are very interesting, and it's based on ideas from proof complexity and pseudo randomness. So there are many beautiful works here. You could also make a PRG conjecture, which is similar to this one, just talks about pseudo randomness. And in this domain, there's a big difference between one-wayness conjecture and PRG conjecture. For example, the kind of predicates for which you can hope for pseudo randomness are very different from the one-wayness assumption. Nevertheless, we were able to show that the one-wayness implies the pseudo randomness, with one caveat. The distinguishing advantage will be only 1/poly. So now I hear that they need 1/poly in obfuscation anyway, but this bothered me for a long time, this 1/poly. It's not about the running time, it's about the distinguishing advantage. And relatively recently, we were able to show a general transformation that takes a polystretch, a PRG with constant locality, with weak security, and kind of upgrade it to polystretch, a local PRG. So this is kind of the state of the art. I was planning to talk about the choice of the predicate, and today we have many insights about how the predicate should be chosen as a function of the length. I'm not going to talk about it, but in one slide, let me tell you that you need two properties from the predicate. One of them is resiliency, which basically means that even after you fix some of the inputs of the predicate, it will still be balanced. Okay, this is kind of, you can describe this property as in terms of the Fourier coefficients of the predicate. And the other one is kind of having high algebraic degree. And this is in order to defeat linear algebra. Now, it turns out that degree is not exactly the right thing. You need something stronger than degree, namely, even after you fix some of the inputs, the degree is larger. In fact, even this is not enough. You need some stronger variant of degree, but I don't have time to talk about it. So let me skip this part and go and conclude. Okay. SXDH, it's an assumption of bilinear maps. Don't have time, but it can be broken by quantum adversaries, right? And it's a decisional assumption. Good. So let me kind of try to look at the picture again. So we have this cryptomania assumption, the LW, the SXDH. We have these mini crypt assumptions. One interesting thing for me is the fact that these two kind of assumptions were studied. The original motivation was kind of the complexity of crypto, or kind of theoretical questions about arithmetic cryptography, things that were kind of directed by basic questions about efficiency, and not about, and the motivation was not to get like stronger cryptographic tools, right? In a sense that stronger functionality. And for me, it was kind of surprising to see that, you know, these are, in a sense, the missing pieces together with public key assumptions that give you this thing. I'm surprising, but actually I shouldn't be that surprised, because we already know, at least in the context of MPC, and there's a paper, the ICOS, one of the ICOS papers of Yuval, Eyal, Amit, and Ostrovsky, that shows you, at least in the context of MPC, that if you have like, you know, cheap mini-crypt assumption, it can help you with MPC, right? I mean, it helps you to boost things in a way that that is useful and non-trivial. So I don't know, this is one interesting take-home message. I think that it's very interesting to try to order these things, at least for yourself. And this is very subjective, but let me suggest one way to order things. So think about the level of homomorphism. So if you think about an encryption that is based on this local PRGs, you get no homomorphism. If you use this LPN, you can basically add, you get addition, but bounded addition. You can add a bounded number of messages before the noise exploits. And then it's bounded in sublinear actually in the number, in the dimension, right, in a sense. SXDH, well, you can do bilinear things, and LW, as we know, you can do basically everything, right? I mean, fully homomorphic encryption or layered homomorphic encryption, you can do many things before the noise explodes. Good, so that's it.
Thank you, Benny. And yeah, I think, by the way, that probably you can find different criteria for any one of the 4 factorial permutations between these.
I totally agree. I totally agree. But you know, it's kind of find the reasoning that convinces you, not just something that works. Right?
Yes.
But I agree that actually this is one thing that is really like annoying, that we don't know how to order assumptions, and it's a kind of, it's a multi-dimensional game, right? I mean, it's not clear that there exists an order.
But maybe that's like something to discuss in the panel. Maybe are there any questions on the talk?
Great talk.
Okay.
Thank you.
So if there are no questions, maybe what we'll do is we'll break for just 4 minutes.